Hi everyone. So today we are going to talk about probability models. So in the last lecture, we learned about random variables. In particular, talked about discrete random variables. But today, we are going to talk about continuous random variables. And there are probability models for these continuous random variables. For a continuous random variable, the probability is defined as the area under the curve over an interval. So like this, we learned about the 68, 95, and 99 7 rule, right? The 1 SD is around 68%. And that is the proportion of the area under the curve, and that is a probability. And there's no area for a point, and therefore px equal x equals 0. So this is quite different from discrete values. We can only define the probability using the interval, for example a and b, and we call this px less than x as cumulative probability. So there are multiple probability models that are very useful, and normal model is actually just one model among many. In this lecture we will go over the following models. We want to start with a geometric model. To know the geometric model, we first need to know the Bernoulli Trials. So there is a snack box. The snack box has some interesting cards. For example, the Pokemon card. There are very cute but not that strong cards like that. If my kids get this, they should think about the failure. But there is a really strong card and rare card that is success. So let's say the success rate is 10%, then the probability of success is 0.1. And there are two possible outcomes here, success and failure. And each trial, purchasing snack boxes and getting the card, are independent of each other. So these type of things are Bernoulli trials, and there are other Bernoulli trials like tossing a coin and shooting free throws. There is a success and failure, two binary choices, binary categories, and probability. Each trial is independent of other trials. So there is a geometric model. In Korean, it's 등비 model. And that's about this question. How many snack boxes we'll need to open to find the success card? And we know that the probability of getting this card from one box is 0.1. And let's say we got that card in the second box, and then the probability becomes the first card should be failure and the second box should be success, and then the probability for that is 0.9 times 0.1. And let's say if I get the success card in the fifth box, the probability of getting that success card in the fifth box becomes this, like this. Multiply 0.9 4 times and then times 0.1. And if we plot this across many boxes, many numbers of boxes, it looks like this. And actually I made this plot using this code, MATLAB code. I used MATLAB code because I'm most familiar with this MATLAB. And here the probability is 0.1 and Q is 1 minus P, so equals 0.9. I assume that there are 100 different cases. The probability of getting the success card in nth box can be expressed like this. And I plotted that, and this is actually the expected value because this is nth box, and then times probability and get the sum of that, and the expected number of boxes to open to find the Charizard success card is 10. But how I can get this? There's a model for that. So geometry, this we call geometric probability model. The P is success rate, and depending on the success rate, the probability density function looks quite different. So I made this plot using this code. So if you have MATLAB on your laptop or computer, you can actually try to run this. But it doesn't matter. It is not important know how I ran this, but the important thing is the concept. So probability here is probability of success, and therefore Q, the probability of failure, is 1 minus P. As we just went over, the probability of getting that success on X is this. And the expected value is 1 divided by P. And the standard deviation becomes this. And you can actually use these functions, GOPDF, this is probability density function or cumulative density function, to use this geometric model. And also you can use these in Python, in SciPy toolbox. For example, for the geometry GOPDF function in MATLAB, 2 inputs. One is X and one is P. From this, you can calculate the probability. And this is the proof why expected value of X is 1 divided by P. So this is what we know, right? So X equals 1, it's P, 2, QP, and 3 is Q square P, and so on. And expected value should be 1 times P, and 2 times QP, and 3 times Q square P, and so on. And actually we can replace the P with Q, and 1 minus Q, 1 minus Q, and then it becomes 1 minus Q plus 2Q minus 2Q square plus 3Q square, and so on. And because this is cancelled out, it becomes 1 plus Q square plus Q to the 3. And as we learned in high school about 무한 등비급수, we know that that's 1 divided by 1 minus Q. So finally, it becomes 1 over P. The second model is binomial model. So suppose you bought 5 boxes of snack, and what is the probability that you get exactly 2 cards, 2 success cards from those 5 boxes? So still this uses Bernoulli Trials, but different question, the number of successes in 5 trials. And there are 2 parameters for this binomial model. One is N, that is number of trials, and P is the probability of success. So 2 successes in 5 trials means 2 successes and 3 failures, and the probability of that defined as this. So there are many combinations of 2 successes and 3 failures that are possible, and we use this combination and choose K, get the cases, the number of combinations. As you know, this can be calculated with this. So in binomial distribution, the P X equals X, that means among the number of trials, what is the probability of getting X number of success? That can be expressed like this, right? And the mean becomes MP, and standard deviation becomes square root of MPQ. That means variance becomes MPQ. So probability of number of success 2 equals, among the 10 trials, is 10 times 0.1 square times 0.9 and cubic, and that becomes 0.0729. We can also draw this binomial probability function using MATLAB. You don't need to know the details of this code, but I did this. And then depending on the probability of success rate, the shapes of the binomial probability function looks really different. And this is the cumulative probability model. That is, as I said before, this is the cumulative probability function. And we can code this using this code. And there is also the functions for binomial model, Bino PDF and Bino CDF. CDF is a cumulative density function in MATLAB and also in Python. Most of the computer programming languages have these models already implemented. Then why the expected value binomial model is P? These are the proof. So to derive the mean and standard deviation of a binomial model, we need to start with one trial, just a single Bernoulli trial. For one single trial, expected value is just P, right? Because 0, failure, Q, and 1 success, P. And then if we calculate the probability expected value, that becomes P, and the variance becomes PQ. We learned this in the previous lecture. Now there could be more than one trial, and then given that each Bernoulli trial are independent of each other, we can use those equations, rules, to solve this problem. So expected value of the combination of the events, it becomes MP, and variance also becomes MPQ because they are independent. Standard deviation is a square root of variance, so square root of MPQ. If you see this plot, the binomial probability density function, some of them look exactly like the normal distribution, like this and these, right? It's perfectly bell-shaped. Usually, when n times p is larger than 10, or n times q larger than 10, the binomial model is approximately normal, so that we can simplify the calculation of the probability. So when we didn't have the computer, this type of approximation was very useful. But now, given that we have computers, very high capacity of the computational resource, we might not need this, but it can be approximated with normal model. And third one is Poisson model. It's closely related to binomial model, but there could be rare events. So huge number of the events and a couple of numbers can happen. So in that case, binomial probability could be difficult to calculate when n is too big, because you should calculate n factorial. So Simon Denis Poisson derived his model to approximate the binomial model when n is really large and p, the success rate p, is very small. And there is a parameter we use, the lambda, that is defined as MP. Because n is really large and p is really small, this has reasonable range. In that case, the probability of having x number of success becomes like this. So this is an approximation of the binomial distribution. So the Poisson model is reasonably good approximation when n is larger than 20 and p is smaller than 0.05, or n is larger than 100 and p is smaller than 0.1. And there are some other models. One is uniform model, that is each point has the same probability, and the probability between C and D within the interval AB, we can calculate that like this because it's an area under the curve. It's simple, and the expected value is a plus b divided by 2, and variance becomes like this. For this, I'm not gonna provide a proof, but you can easily find the proof online. And there's the exponential model. The Poisson model is a good model for the interval or occurrence of events, but sometimes we need the time between the events, between the arrival. So for example, we can use the Poisson model to model the probability of X visits to our website within the next minute, but we can model the time interval between the visit using the exponential model. So here lambda is still MP, and the probability density function is defined with this equation. And the mean and standard deviation of the exponential is 1 over lambda. The probability of interval defined by this, it's very, very convenient, and cumulative density function is also simple. Okay, so in this chapter, we learned about geometric model. For that, we learned about Bernoulli trial, and binomial model, and also Poisson model, and uniform model, and exponential model. So the important concepts are probability density function, that is basically P is x equal x, or interval. And cumulative density function, that is this, and mean and standard deviation of each probability density function. That's it for today's class, and don't forget to complete the quiz. Thanks. See you in the class.